on the other side, and I can see my phone is back to, because they were working on the networking equipment, and now I got caller ID because I didn't have caller ID before. All right, excellent. Let's start this class. All right, first thing first. Let me go back to the test, exam 2, the practice exam 2. I think I found a better way to keep track of things, so this way it is easier for you guys to answer those questions in the first one. I'm not streaming. Oh, right, because I forgot to turn on the screen share. Okay, that was an operator error. Networking is up already. I just forgot. That's all. Thank you. Thank you, Richard, for reminding me to stream on Discord. And then on the other side, I think things are doing okay. Terrence is typing something. I'm gonna hold on to that a little bit. But I do want to show you, this is basically it's an easy way to keep track of things. Basically, we have two sections here. So with every single step, we have one section that talks about the nodes, and then each node has a single value. So initially, everything is unknown. But in question number 1, A gets a value of 1, and then B gets a value of 0. So this is how we spread the this is how we find out what value each particular pin or each particular port of each component is getting. And then the rest are all basically unknown at this point, and then we have to figure out what the rest are going to be. So this is an easier template, and you can just kind of copy and paste it and just make changes as you make copies of this. So knowing that p.in 0 is changed, so we need to look at p. Oh, okay, I forgot about p is a component here. So here's p. So now we need to take a look at p.out, because this is a change. So in your test, you can make you can highlight this with I guess with boldface. I can't really do it here. I suppose I can put an asterisk here to make it to say that this is changed from before, and so is that one. So p.out is still going to be unknown, because even though we know one of the input pins is a 1, because we don't know what the other one is, so we still don't know what is p.out. So p.out is still unknown at this point. There we go. All right. I'm not sure if it will work inside a block, because this is inside a block here. So as a result, everything is just verbatim, and I can't do this outside of a block, because if I do this outside of a block, the square bracket is going to be interpreted as hyperlinks. So there are some restrictions here as to what I can do, to note things. So but basically the idea is just that. Okay, anything that has an input connected to something that has changed, we need to look into that. So p is 1, and then we also know x is the other one. So we say x. We know x dot r is a 0, so we know x dot nq has to be a 1, because x dot r is a 0. But we don't know what is x dot nq, because we need to know what is x dot s in order to answer that question. And then x dot s is, okay, let me see, did I even track that node? X dot s is connected to p dot out, and it's not even tracked at this point, so I'm gonna have to track that too. So so there's a particular convention here that I'm using. Basically, I use p.out, whatever the output pin is going to be the first item, and then whatever it connects to, which is going to be an input port, is going to be the second thing here. So that's so basically, this is a way for you guys to answer questions like the first one in the practice test, in a much more systematic way, because now it's easy to keep track of these things. So with the devices, and then we can say x dot q is unknown, because x dot s is unknown. Okay, let's move on to y. So y is not changed. Actually, y is, okay, because y dot r is a 1. But something being a 1, just the reset pin being a 1, doesn't help us in any way. So that means y dot nq and y dot q are unknown, because y dot, the only thing we know is y dot r is a 1. Y dot s, which is over here, is still unknown. So this is, so now, in order to do the next step, if there's a next step here, there's no next step here, okay? Because actually there is, because x dot nq is changed. So so the next step is just copying and pasting this entire block here, but only noting what changes we have made. So the only change we have made here is x dot nq being a 1. So we change x dot nq y dot s to a 1 here, and then denote this one has been changed. And then the other ones we want to undo the asterisk because we don't want to repropagate those changes. And then from this part here, when we do the analysis, y is potentially the next one that can have an output or have a change. So these we can kind of get rid of. And then y is the one that we have to analyze this time because one of this input got changed. So yep, that is what I want to do. Alright, so in this case, what do we know about y? Y dot s is a 1, and then y dot r is a 1 as well, so it's just maintained. And so we just have to say y dot r, y dot s are both 1s, but we still don't know what is y dot nq or y dot q because it's just maintaining its current state. So as a result, nothing is changed because of this propagation, and that concludes the first step. All right. So that's just a new, another way to keep track of your changes. And because this time we are listing, all of the nodes and also all of the devices here, it is easier to keep track of things because, once we have determined one of the output pins, it's going to show up here, and that makes it easier to figure out what is the current state of something. We don't have to search backwards insanely in order to find out, okay, what was the last thing we did about this particular output port. We can just look it up and quickly find out. Would you want us to indicate that no changes happen? You can have a notation, NC, to say no change. So anything that has a no change is basically a dead end. There's no further propagation that you need to worry about because it is maintaining whatever it was before. So is that answering your question, Richard? All right, excellent. All right, so just wanted to get back a little bit to what we talked about in the previous class, just so that when you encounter a question like the one in the practice test in question number 1, now there's a much more systematic way to keep track of things. Basically we look at each node first, and then if a node is seeing a change, then we look at the device that has one of the inputs impacted by that change, and then we ask, okay, how is that device going to respond to that change of the input pin? And then if the device does not change anything with its output, then we go like, okay, that's a dead end. If on the other hand, if the device changes its own output, then we have to continue with the next phase because one of the output pins got changed, and then it will propagate through using the nodes. So it will just be alternating between node, device, and so on. Alright, so Terrence has 2 questions. So for every phase of the analysis, we just copy and paste all of that and update. Yes, for the most part. The only thing is you probably have to, with the devices, you probably have to delete, what you have copied, and then reanalyze, if there's anything to analyze. So this is the part, the devices part is the part where you have to refresh every single time. So you might want to keep an empty devices list, with just the devices, but not what has been changed. So this way you have basically you have a fresh list that has nothing in it. So you don't have to go back and keep deleting, whatever was changed before, so that you can you can have a clean list to begin with. The other one, the nodes, this one is just copied and pasted for the most part, unless the devices has changed one of its output, then you have to update this one as you kind of copy and paste to the next one, to the next phase. The next question from Terrence is, do we need to say anything about propagational delay? This is basically the changes after a propagational delay. So you can always say devices after propagational delay. So you can kind of mention that, but that was kind of implied when I have that one. And then Matty has a question for number 2. At one point in the last class, you said that we are assuming the Z flag is a 1, had to do with analyzing the PC. Not really sure about that. Alright, so that has to do with the conditional branch. So when okay, so let me go back to Logisim first, because it's a whole lot easier to explain it when we look at the circuit diagram. Alright, so this is Logisim, and let's use one of the conditional branch instructions. I'm not sure whether we're still at that point or not. Yeah, I just kept the computer running the whole time. So let's see, this is okay, so we are not looking at a conditional branch instruction. Let's put in a conditional branch instruction. Let's see, I think for 1 is a conditional branch instruction, right? For 1. And there's a way to quickly get to the microcode of the conditional branch instruction, which is hard coding something into the microcode pointer. So for opcode 41, where do you think I should point to in order to understand how things are connected in the processor? This is a question, okay? This is me checking whether you guys have understood the concepts, or well, actually not even concept, understood how the processor is connected. 410 is correct. That is right. Terrence is correct here. So I'm just going to put in 410 here. So now suddenly we are now at the microcode slice, which is just a location in ROM, that will dictate how things are connected and which one is active and which one is inactive. So over here, when we look at PC mux, it is a 4. So this is not exactly JZI. This one is actually JLI, because bit 4 coming from the flags register is the L flag. So getting back to Matty's question. Okay, so Matty's question is, why make the assumption? Because, well, it's not exactly an assumption, because we need to somehow figure out, how the register is updated. We know PC is going to be updated. We know that because PCEN is a 1. So the next thing we need to do is to find out, how PC is going to be updated. So the problem with that, the difficulty of stating how PC is going to be updated is it depends, okay? Because right here it is coming out, whatever is going to be updating the program counter is coming out of this multiplexer. But because this is a multiplexer and the control or the select pin of this multiplexer is PC mux. Now PC mux is right here. In other words, PC mux depends on bit 4 of the flags register, which sometimes is a 1 and sometimes is a 0. So you now have to now if you recognize what this is doing and it's doing a conditional branch, you can just write use the ternary expression to say that okay, if the L flag, which is here, is a 1, then PC mux is going to be a 1, and if PC mux is a 1, then we are going to be reading from the data port from RAM. On the other hand, if the L flag is a 0, then PC mux is also going to be a 0. If PC mux is a 0, then we'll be using input 0 to connect to the output of this multiplexer, which means we're just incrementing the program counter. So I think what Matty was referring to was a part of the analysis of what if the Z flag is a 1, and then the other part is what if the Z flag is a 0, because the Z flag is entirely dependent on what was stored into the flags register from some previous instructions. Is that answering the question, Matty? Because I cannot remember. Oh, okay, sure. Okay, because I cannot remember exactly the phrasing nor the context. When I said z equals to 1, but I would assume that when I said that it was to play out one of the two possible scenarios, because these 5 bits, they come from a register, and depending on the content of the register, these 5 bits can be zeros or ones. Oh, okay. Yeah, absolutely. So the key to study for this test, especially for something like question number 2, is really thoroughly understanding every single component of the processor and understand how they connect with each other. But the connection is not a problem. The connection is all laid out in Logisim, so you don't even need a printout if you have I mean, okay, that was a stupid question, because I was saying, if you have a computer when you are taking the exam too, of course you have a computer when you're taking exam too. This is all online. So unless you're using something that cannot run Logisim, okay, I suspect there's even a way to run Logisim on the Chromebook. So bring up Logisim, bring up the processor, so this way when you want to analyze a node, you can quickly and very easily find out how a particular node is connected. So use Logisim to help you with the analysis. It doesn't replace quote unquote studying, okay? Because when you're quote unquote studying, when you're trying to figure out instructions that we have already talked about, that would get you familiarized with the locations of stuff. It's just kind of like you let's say you're driving Uber, and if you don't prepare anything and you just rely on the GPS, to get you to places, that's gonna, sometimes it might get you to places, and sometimes, it may not get you to places. On the other hand, if you have been driving around in the Sacramento region for a while already, you don't even need the GPS, right? I need to get to, downtown and this hotel. You go like, yeah, I know exactly how to get there. So that's why, to study for this class is really to examine the opcodes that we have already talked about, and some of the ones that we may not even have talked about, and then just use that to help you practice how to analyze the output coming from the ROM, and how those bits, individual bits, is changing the connectivity between the components inside the processor. All right, so I'm getting back to the text channel. Okay, so getting back to Colton first. When it comes to the value of NC, node connectivity, what method do we use to find its value? So NC, okay, this is, so Colton's question goes back to this slide over here. Um, and the answer to that question is it's either coming from the question itself, like when I say pin A is now changed to a 1, then the node connected to A is going to be changed to something. Okay, so that would trigger a change to one of the input pins. And then the second thing, let me see. So the second thing that can trigger a change is because a device, in response to one of the changes to one of the nodes, a device after a propagational delay, changes its output. So when a device changes its output, and if you look at these node lists here carefully, the first item within this list is always an output pin or an output port from a certain device. So that makes it easier for you to identify, oh, okay, let's just say that p.out is changed here. So when p.out is changed, you look up this list here and say, oh, okay, if p.out is changed, this entire node is going to be changed. So you now have to update whatever value this node is known to be at the time, and then say, okay, now we know it is a 0 or 1, and as a result of that, x.s is going to be changed, and then you have to remember to update x, or at least analyze x, because we know one of the input pins of x is changed, and as a result, after a propagational delay, the outputs of x may be changed as a result of that. So I hope that answers Colton's question. Let me know if I did not answer the question. Okay, while Colton is writing, I'm going to get to Terrence's question. Can you explain when we would want to use JMPI versus JLI versus JLX? Okay, so JL is an interesting one. It is like a JLI, but without using the immediate constant. So it would use a register to determine where we are supposed to be going. Um, it's not going to be very useful, but if you want me to explain in the context in which each one is useful, the JMPI is easy. JMPI is a unconditional branch, so it's basically saying, okay, I don't really care about the flags. I'm going to branch. Okay, and that is needed because sometimes we need to change the polarity of the conditional branch. So, sometimes we want to branch when something is less than something else, and other times we want to branch when it is not less than something else. So JMPI gives us the flexibility of inverting the logic of the conditional branch. Now, on a more sophisticated processor, they would have JLI and then a JNLI, which is jump if not less than, and an immediate. So you can change the polarity by changing the opcode itself. But TTP is as simple as it gets. Okay, so any extra instruction that is really not necessary and it's just eye candy, I try to prune the eye candies as much as possible. So I'm not sure whether that answered Terrence's question or not, and if Terrence can confirm one way or another, it would be great. But I'm moving on to Richard's question next, which is, so judging by the sound of it, for our full answer for question 2, we need to state both scenarios with the flags 1 and 0. The answer is you can use the ternary operator, right? Because the ternary expression is going to answer the question exactly. So let me switch to question number 2. So the way I would answer the question is to capture the logic of the conditional branch using a ternary operator, which is basically saying, if the z flag is non-zero, then we utilize whatever the program counter is pointing to in RAM to update the program counter. If the z flag is indeed a 0, then we're gonna just use whatever the program counter is, add 1 to it, and that's how we update the program counter. So you can always change this, right? You can always change this notation to say if z equals 1, then blah blah blah, and then you can say else, then blah blah else blah blah blah. Okay, so you can turn it into a conditional statement, to separate the two cases and say, okay, if the z flag is a 1, then this is how we update the program counter. Otherwise, the program counter is just the program counter plus 1. So either notation is considered 100% correct. So this is just a more concise notation, and it is also utilized in column C of the opcode table. And this is a much more spelled out version of the previous one. It is still correct. It's still 100% correct, but it makes it a little bit harder to match this description with column C, when you need to find out which opcode closely resemble the microcode that you're given with. So that's just that. All right. So we're getting back to the text channel. Colton says, so when it comes to finding the value for NC, the node connectivity, if we run into a value that outputs something, okay, that changes its output, we are only looking for changes. Okay, if a device is outputting something but it is the same as before, then it does not trigger a change that we need to denote in the node connectivity. Okay, so we are only looking for changes. If a device changes its output from a 1 to a 0, or from an unknown to either a 1 or 0, then it will trigger the next phase, because that would also be fed into some kind of input port, which can potentially trigger another device to change its output. So we have to track the changes. But if we know that what all the outputs of a particular device do not change, even though its input is now determined or changed, then it is still a dead end, because it is not going to trigger any further changes, and there are no more analysis to be done for that particular step, at least for that device. All right, so Terrence said, you pretty much answered my question. Okay, I was curious how we would use them when writing programs for TTP. Oh yeah, that's kind of what today's lab is about. So, if we can get to the discussion of what we are about to do in today's lab, you will actually see how JMPI, can be useful. All right, and then Jonathan W said, why is PC equals to star PC? I thought PC equals star PC. Oh, that's just a spacing issue, right? And also, whether the parentheses are inside the asterisk or outside of the asterisk. So that doesn't make any difference when it comes to whether the reference is going to happen either way. It's just the notation is a little bit different. So I think Jonathan W is talking about this versus this. They're really the same thing. All right, so Richard is typed in response to your question. Wouldn't that mean we can just state the ternary operation or expression as our answer? Yes, absolutely. Yep, you can just go with this one. If you recognize this is what it's doing, then you can just use this notation here. Wouldn't we need to mention the other components that determine what it is we are given? Oh, you mean to explain, why this summarizes, the operation? Yeah, you kind of have to mention that, your PC mux, is determining, which bit is connected to PC mux, and as a result, PC mux, changes determines, the multiplexer that feeds into the program counter's D port. So just kind of briefly explain, how the connectivity is making you conclude this is the outcome of the operation. All right, so I think I'm all caught up in the text channel. All right, very good. And by the way, this is why I teach, in synchronous mode, because, this way, you guys can ask a question and I can answer right away. And then guess what? The rest of the class can also participate, because one question may trigger a person to go like, wait, hold on a second here. Since you're asking that question, that reminds me of blah, 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 and I want to ask that too. So this is perfect, for that type of interaction, for a class discussion, an actual class discussion, and not through a forum where there's a propagational delay. Yes, I like to use that term. There's a propagational delay when you're using a forum, but when you're using Discord, well, there's still a propagational delay, but it's a lot shorter. All right, cool. We are all caught up here, and we're going to change to today's note. This is one thing that Joplin is kind of really cool, is it maintains notebooks. So within a notebook, you can have multiple notes. So to change from note to note, you just have to use these two buttons here to kind of go between the notes of the same notebook. When you have a lot of notes, from the same notebook, I can see how that can be a little bit tedious. But right now, we only got a few, so it's not a problem. All right, cool. So what we'll do today is we're going to look into some C code, and now outside of the context of a function, outside of the context of variables, local variables, and so on. So at this point, we just want to kind of focus on, okay, let's try to do everything with registers and not worry too much about, how we allocate memory for variables. Now, there are several reasons why I want to defer that discussion. The first one is we haven't really talked about the stack yet, okay, which also means we cannot talk about local variables. So the only kind of variable I can talk about right now, would be global variables. So yes, we understand enough already at this point to talk about global variables. But there's a reason why I don't want to talk about global variables, because generally speaking, they are not very good ideas. I'm not kidding, okay? If you're writing a program and you say, okay, I need these, global variables for the program to work, you might want to rethink it, because there are usually ways to avoid the use of at least a whole bunch of global variables. They are very convenient because you don't have to pass, something as a parameter into a function, so the function knows about, something. But at the same time, your code is going to be more brittle because, if you ever want to make that function more modular, then, the dependency on the global variable, makes it not very modular anymore. Um, Class variables, we'll actually get to that, sort of. Okay, we'll get to structs, we'll get to structures and members of structures. So what Jonathan W just said, your class variables, that would be a member inside the structure. So we will get to that. We'll also get to local variables as well. Okay, so we'll get to all of those topics, but for now, we're going to focus on just registers. So I'm going to give myself an assignment here and say, I want to see if a register has a value that is divisible by 2 or not. If so, I'm going to do one thing. If not, I'm going to do something else. So to check whether a register, okay, let's just pick a register. Okay, let's pick register B in this case. So we're fixating on register B, and we are asking, okay, let me put it in actual C code here. So we are basically saying, if this is the C code, okay, and B in this case, I'm going to make it even more clear. If register B is divisible by 2, okay, I'm going to say divisible by 2, then we want to do one thing, and this is going to be a halt instruction. And then we'll say, otherwise, we want to do something else, which is also a halt instruction. So these are two different halt instructions. But that's what we want to do. So the first thing we need to do is to say, but how do we know whether a register, with one of the 4 registers, is divisible by 2 or not? Do we know enough to do that already at this point? Okay, so that's the question. All right, so I am going to let you guys think about this a little bit. Okay, if you have the answer, don't type it in the text channel just yet. Okay, you just kind of hold on to your thoughts, okay, because I want everybody to have a chance to kind of think about this. And while you guys are thinking about it, I'm going to give you some clues of what you can think about. Okay, so let's take a look let's take a look at everything that kind of have to go through the ALU, because we kind of know that determining whether something is divisible by 2, is going to involve some kind of calculation, and the ALU is what we need in order to perform calculations. So now the question is, which one are we going to use? So we have add, we have subtract, we have compare. Compares CMP, which is basically subtraction but without storing the result. We have right shift. We have arithmetic negation. Not arithmetic, this is bitwise not. We have and we have or. Okay, so these are the 6, 7 instructions that actually make use of the ALU. And then we have increment and decrement. Okay, so increment and decrement are basically just adding 1 or subtracting 1 from a register. So start with these. Okay, start with these and say, okay, how can we use just a combination of these things in order to figure out whether the value that is stored in register B is divisible by 2 or not. Whew, okay. So let me catch up with the text channel while you guys are thinking. What are we thinking about? I'm sorry, I'm paying attention, but just didn't hear that I had water running. Oh, okay. So we are just trying to think about, how to do this, but using TTP instructions. Okay. And the TTP instructions that I think would be kind of useful would be these guys. And obviously, in order to do something only sometimes, and sometimes we're going to do something else, we're going to use some JXI here. Okay, we need some kind of conditional branch, and every time we use conditional branch, we probably need to use some unconditional branch as well. So these are the things on your tray. The question is, how do you arrange these things in order to implement the logic that we want to implement over here? We don't have modulus. That is correct. So Matt is correct to think about modulus, but Jonathan W is also correct that we don't have modulus. But division by 2 is special, okay, because we're dealing with base 2 numbers, right? So division by 2 is special. I'm just gonna say that and let you guys kind of think about it a little bit, because we can use bitwise operations, for some of the base 2 type of operations. So multiplication by 2, division by 2, finding out what is something mod 2, those can usually be done using bitwise operations. All right, no problem. Yeah, so or you can translate the modulus operator to something that is a bitwise operator. All right, so to give you guys a clue of those things, I am going to give you the equivalent C operator. So right shift is just that. This is bitwise not, so it's a tilde and not an exclamation point. This is bitwise and, so it is an ampersand instead of ampersand ampersand. This is bitwise or, which is just a vertical bar. Increment decrement, I think you guys know those two already. So these are the operators that we can implement, okay, that we can make use of, pretty easily, because they are native to text toy processor. All right. I'm just keeping track of the conversation in the text channel. Not a whole lot right now. All right, so Terrence says, so we don't even have division. That is correct. We don't have division. Division can be done using just comparison and right shift. It's in base 2. So if we are interested and if we have time, we can talk about, how to implement division using the operations that are already supported in the arithmetic and logic unit. And then Ivan said, should bit 0 be 0? That is correct. Okay, so that's a very good clue. Okay, every number that is divisible by 2 has bit 0 being a 0. Okay, that's a very good starting point. Jonathan W said, yeah, I suspect we have to use the shift somehow. Well, the answer is actually we don't need to use the shift. We don't need to use the shift. So RSH is actually not needed in this case. Terrence says, so then we can just compare with a 0. Well, we can actually do better than that. Okay, we don't actually need compare. Okay, so that's the fun thing about this. Okay, so there's so so um, so to answer the question, to kind of come up with a solution, it is a matter of looking at values in base 2 and then figure out, okay, what bitwise operations do I need to do? And then when we figure out what bitwise operations we need to do, to figure out whether a value is divisible by 2 or not. And then what we do next is to think about how each instruction makes use of the processor resources, like the AND thing here. It's going to come in handy, okay? And I said, we don't even need a compare after that. And that has to do with inside the ALU, there are 2 bits that are always changed because of the result of an operation. And those 2 flags, one is the Z flag and the other one is the sign flag. Okay, so those 2 flags are always affected. The other flags, like the B, the borrow, which is also known as the carry flag, the sign flag, the overflow flag, and the L flag, those are only changed by these 2 instructions and also this one. But every single one of these, other than increment and decrement, would also affect the Z flag as well as the sign flag. So how do we make use of those things? Okay, I'm gonna go back to the text channel and catch up over there. Alright, so Richard said, I have a sneaking suspicion that we need to examine the first 2 bits. Almost right. You're half right, because we only need to examine the least significant bit. Okay, we somehow need to isolate the least significant bit of register B so that we can see whether it is a 0 or 1. So Richard is on the right track. Jonathan W said, oh, so bit 0 of register B has to be 0 of 2. No, it just needs to be a 0. No, we're not going to use a splitter, okay? Because a splitter is something that you can do in hardware. We're trying to figure out using software. We're trying to use a sequence of TTP instructions to do this. Bitwise OR is only good if you want to set something into a 1. Okay, we are not trying to set something into a 1. We're trying to check whether something is a 1 or 0. We're trying to isolate a particular bit to see whether it is a 1 or a 0. Alright, so I'm going to give you guys the answer, unless you guys said, okay, give me some time. I'm really, really close to the answer. So if someone needs a little bit more time to kind of complete your solution, let me know. All right, nobody is asking for a little bit more time, so I guess you guys are ready for the for the answer. All right, so the answer, I'm gonna give you the answer, but I'm gonna give you the answer in phases. Okay, so instead of just giving you the answer right away, I'm gonna break it up and say, okay, let's think about it in C code, just C code for now. So what we want to do is to say, how do we know whether register B is divisible by 2 or not? So we can say, oh, well, if we had the mod operator, it would have been easy because we can just say, hey, reg B mod 2, if it is 0, then we know we get to the first halt instruction, and then else we get to the second halt instruction. All right, so that is good. Okay, that's a good first step, to get to the answer. And I have no idea why this halt has the extra indentation and then the second one does not have the extra indentation. Probably a bug of Joplin. Can you just add 1 or subtract 1, then determine what it would be by the opposite? Well, I can do better than that. So when you are doing a mod 2, when you're dividing by 2 and you just want to know what is the remainder, it's the same thing as bitwise AND with 1. Let me just write the code and you guys can see it. Okay, so this is the C code. All right, so all of these programs are logically the same, even though they are implementing something differently. So in this case, I'm just going to say reg B and using a single ampersand with 1. And we need that to be a 0. Okay, so I'm going to put extra parentheses just to make sure that we are looking at the result of the bitwise AND and see whether that in return is a 0. If so, we have a halt. If not, we also have a halt, but the two halt instructions are distinct. They're different halt instructions. All right, so now we're going to look at this. Okay, we're going to look at this, and then we're going to look at this. And quite clearly, this is implying that reg B mod 2 is the same thing as reg B bitwise AND with 1. So whether this makes sense or not and how to look at this, the best way to look at this is to use concrete cases. Okay, so we're going to work with some concrete numbers, and let's start with 5. Okay, so I think here I can, okay, my cat wants to get outside. I am the official door opener for my cat, and he's hesitating right now. Hey, you want to go outside? No, he's hesitating, so I'm going to close the door. There we go. All right, so we're going to look at 5, right? Okay, so 5, and I'm going to use equation here. Mod is an operator, so that's why, okay, it's supposed to turn it into mod. Suppose I can use percent here. So 5% 2 is, well, we know what it is. It's a 1. And it's not converting this into equation. Oh. That works. And single dollar sign does not work. That is very odd. And then the mod, I think it needs a backslash because a percent is a, maybe that's why. There we go. Right, the space also, kind of interferes too. So there we go. Okay, I like it better this way. All right, so 5 mod 2 is a 1. Okay, so that's good. And what about 5 bitwise AND with 1? What is that? It doesn't like that because the ampersand needs to be escaped. There we go. It's going to be a 1. Now, how do we know that, right? How do we know 5 ampersand 1, which is bitwise AND with 1, is also a 1? Well, we can look at it, using, actual expansion. So we can look at 5 as a binary number, which is 101, and then we line it up with 001, and then we say, okay, let's do a bitwise AND. It's better to look at this side here because everything is lined up. So if you perform a bitwise AND, that means the result each bit of the result reflects the result of an AND of the corresponding bits of the operands. Okay, let me say that one more time. So in the result of a bitwise AND, in each bit of the result of a bitwise AND reflects the conjunction of the bits of the same position of the operands. Okay, that's a mouthful, but it is correct. Okay, so now we look at this and we say, what is 1 and 0? Let's work with the most significant bit first. 1 and 0 is a 0. 0 and 0 is a 0. 1 and 1 is a 1. So it does work out. Okay, so the result of 5 and 1, 5 bitwise AND with 1, is 1. So there you have it. Okay, and the mechanism, the reason why it works really has to do with, we are working with base 2 numbers to begin with. So bit 0 of a base 2 number is telling us how many 2 to the power of zeros do we have. Then you go ask, but how can we be sure that that alone can determine, whether the number is an odd number or even number? Because all of the other bits will contribute a even number to the value that we are trying to represent. Because the next bit, which is bit 1, is contributing a 2 or 0. The next one is contributing a 4 or a 0. The next one is contributing an 8 or 0. And you can see all of those are powers of 2. So any power of 2 where the exponent is an integer and it is greater than 0 is only going to contribute a even number. So that means in order for a binary number to be an odd number, the only bit that matters, the only digit that matters is digit 0, because that's the only one that can contribute an odd number, which is 1 itself. Is that making any sense? Mathematically? Okay. All right. So now that we know that we can use a bitwise AND to do the job of a mod, because it's a special case, because we are trying to find the remainder of a division by 2. Now, if we want to find the remainder of a division by, say, 7 or 13, or even 10, okay? Even 10 is hard, okay? Because 10 is not a power of 2. That gets a little bit more complicated, okay? But since in this case, the divisor is a 2, it is easy, okay? Because and actually it's not just 2. Anytime your divisor is a power of 2, it's going to be easy. So if it's a 4, if it's an 8, if it's a 16, all of those are fairly easy to figure out, what the remainder is if you want to divide it by a power of 2. Alright, so I'm just gonna repeat this code down there so I don't have to scroll too much. Alright, so there we go. Now we want to think about this and go like, how do we do this in TTP? So the way I work is, I look at what we need to do, and then I just pick out the components and tools and whatnot and throw it into a bin first, okay? Throw it onto a tray, and then I worry about, how to arrange those items in the tray. Now, this is obviously just an analogy, okay? I have absolutely no idea how my brain works, okay? Because if I did, if I did, it would open up all kinds of possibilities, but I don't, okay? So I'm just going to say that, okay, this is I think it captures, how my brain works. It just looks at the rough concepts first, find out what is relevant, what might be useful, and then put it into a tray so that I can focus on just those items and how those items are going to be arranged in order to give us the result that we want. All right, so at this point, we're going to have to identify things that we are going to need. Register B is, well, guess what? Register B, so we don't need to put it into the tray. One is kind of special because one is a constant, and the only instruction that can work with a constant in the context of performing an operation is none. Okay, none of the ALU operations can work with a constant. So we have to somehow get the constant into a register first in order for us to perform an arithmetic operation on it. So that means no, no global variables. LDI, okay? LDI is what we need because we need to put the constant of 1 into one of the registers other than B in order to perform the operation. We have the bitwise AND operation here. Okay, so the bitwise AND operation is just called AND as a mnemonic. So we probably need that. We have a comparison with 0. So for the time being, we're going to say maybe we need a compare. Okay, we can always throw something into the tray and then later on find out, hey, we don't actually need to use it. And because we are comparing to 0, okay, there's only one conditional branch that pays attention to whether the result of an operation is 0 or not, and that is JZI. Okay. And typically, when you have a conditional branch, you probably need at least one unconditional branch because the structure of the code requires you to say, but what if it is not, right? Okay, well then we have to branch around something, and then you need an unconditional branch to branch around something. And obviously, the last one is going to be halt because, hey, guess what? We have one halt instruction here and another halt instruction over here. So this is really just an inventory of what instruction I'm going to need, and I'm using the mnemonic of the instructions instead of the opcode of the instructions because I can't really come up with the opcode unless I know what registers are being used. So AND requires me to specify a register, 2 registers. LDI requires the specification of a register. Compare has 2 registers. JZI is okay, but I need to know where I'm supposed to go. So right now, these things are not exactly organized. Alright, so let's organize things a little bit here, okay, using dependency. So the first thing we need to do is to say, well, before we can even get to the conditional branches or the unconditional branches, we're going to have to evaluate, this expression first, okay? Before we can even compare to 0, we have to evaluate register B and 1. Okay, so what are we going to do here? Well, since we know we need an AND operation here, and I know register B is going to be one of the 2 things that we are ANDing together, the other one is unknown for now. But the unknown is going to be another register, so I'm going to need an LDI instruction to load a constant of 1 into that unknown register. So at this point, we just know that, oh, so that register doesn't really do a whole lot of work other than just being able to store the value of 1 so we can perform the bitwise AND operation. Yep, that's right. So you can use any register other than B itself. Okay, so you can use register A, for instance. There we go. Alright, so now the question is, when you are considering the use of the AND operation, you can use AND BA and you can also use AND AB. The question is, which one should I be using? Does it matter which register we use? You mean for register A, for this one? Okay. At this point of time, anything other than B is going to be okay, because if you use register B over here, then you would have destroyed the value of register B before we got a chance to use it, right? So so at this point, with this particular register, whose the only job is to store a value of 1, you can use register A, register C, or register D. And this is because we don't have a special job for register D yet. The AND opcode returns the result to the first register, so order does matter. That is correct. So Terrence is absolutely correct here. So now the question is, did the original C code say anything about changing register B? When we look at the C code, it does not. Okay, very good. It does not. So that means we don't want to change register B. So we're going to store the result back into register A. We have to store it back into one of the two registers, because we don't have an opcode where we perform an AND operation and not store the result into a register. But in this case, A is basically a scratch pad type of register where it's just a toss away kind of thing. So, nobody is actually going to pay attention to what is in A, after a while. Okay, so right now, we have just completed this operation here, and the result of the bitwise AND is now in register A. So according to this, we want to compare register A to 0 and see if register A is indeed a 0 or not. Matt is asking, so it's like a constant temp. It's more like something that you don't see because in C++ we don't have any construct like how the way we're using register A here. So register A is basically just saying, okay, I'm needed in this operation just because the AND operation requires both of the values in registers, and also because it needs to store the result to some place. So I'm just gonna say I'm that temp guy. Okay, I'm just gonna do this, and then I'll disappear into the background, and don't pay attention to me. Well, Jonathan asked a very, very good question. What if we need a bunch of temp values? Then we have to start to tap into memory. Basically, we only have 4 registers, and if whatever you do needs more than 4 registers, then you're going to have to kind of swap things in and out between the registers and memory. Because even with TTP, we still have 256 locations in RAM as opposed to only 4 registers. So, there might be cases where you need to kind of swap in and out with memory. So it's going to be messy when we have to do that. So far, I have not seen any situations where we have to do that. So 4 registers actually is quite a lot. Okay, you can implement a lot of code with only 4 registers. Next, Richard. Oh, okay, Terrence first. Compare does not store a value, which is intentional. It only set the flags. Yes, it only changes the flags. So we should use a jump based on the flag. That is correct. Okay. I'm looking at the time. Okay, so I'm going to give you guys the long solution first, and then I'll give you the short solution. Okay, so I'll give you a solution that does exactly this, and then later on I'll go like, that's not exactly the best way to do it. I mean, it will get the job done, but it's not, some of the steps is not needed. Okay, so we'll look into that. So somehow we want to compare register A with 0, but we know this is not going to work because compare requires 2 registers. 0 is not a register, 0 is an immediate value, and we don't have a CMPI so that we can compare a register with an immediate value. Okay, so what are we going to do? Now this is why, okay, let me explain why I use TTP, because if I were to just introduce the syntax of the assembly language and explain what the syntax does, then somebody's going to say, oh, Tech, all we have to do is to turn this into an I over here, and now we can compare a register with an immediate. That would make sense, right? Because for someone who understand C and C++ programming, where the syntax determines how something is done, it would make sense to just say, oh, we can just add an I to the mnemonic of the instruction, and now we can deal with immediate instructions. We can deal with an immediate operand. But that is not going to work, right? It's not going to work because none of this, okay, the syntax is not going to change the internal structure of the processor. The pathways of the processor does not allow a path from the D port of RAM to connect to one of the two inputs of the ALU. That path simply does not exist. No matter how you configure the multiplexers and the demultiplexers and whatnot, that path simply does not exist. So that means you cannot use the syntax to suggest oh, we can do it this way, because you cannot. The syntax is only here to help us, to help the assembler put the opcode together, but the syntax alone cannot extend the operation or the permissible operation of the processor. This is why I teach this class in this particular way, because if I had taught this class using the usual way, using the x86 architecture, there's a whole bunch of syntax with that particular assembly language that can say, okay, now this operand is in this mode and this operand is in this mode. It would give people the illusion that it is the syntax that determines what can and what cannot be done, when the answer is no. The syntax is only here to help the assembler put the opcodes together. And then what opcode is possible is entirely determined by the architecture inside the processor, which is what you are seeing over here. And the distinction of, this is the syntax, it is simply here to help us write instructions in a more convenient way, but everything still has to boil down to connectivity between the components, which is entirely dictated by the hardware aspect of the processor. That distinction, I think, is very, very important teaching this class, and that is one of the main reasons why I teach this class using my own architecture, where you can actually see and say that no, there's no way we can implement a CMPI instruction, because there's simply no way, okay, to directly connect the output of the D port of the RAM into one of the two inputs, which is this one or this one of the ALU. Okay, there's simply no way to do it. So I hope you guys are starting to understand why I teach this class in this kind of really weird way, using a weird processor architecture, but you can see everything inside the processor. You can see how everything is connected. Alright, so getting back here, since we cannot do this, we're going to have to say, okay, we probably need a third register now, because we need a third register to store a 0 so that we can compare register A with a 0. Okay, that is a pain in the neck. There we go. So after a CMP instruction, which is essentially a subtraction, but it doesn't store the result into register A in this case, we only need to know whether it's 0 or not. So at this point, JCI is going to come in handy, because JCI says, hey, if we get a 0 after the compare, we are going to branch to whatever you say here. Okay, let's just call that okay, well, I'll just label this as equal to 0. Okay, EQZ for equal to 0. And I'm going to define the label right away at some point, and then write a line of comment just to remind myself, what does it mean when we get to this label here? So we'll say this means reg B ampersand 1 is indeed 0. That's when we get here. So that means if we do not use the JCI instruction to get to EQZ, we have a unconditional branch here, or we can do something over here. So I'm going to say right away and say, if we did not, okay, if after executing the JCI instruction, we are not over at EQZ, what does it mean? Well, it means it is not a 0. So we say this means reg B and bitwise and with 1 does not equal to 0. Okay. So now we have to figure out, okay, what should we do here and what should we do over here? So because both instructions are halt instructions, it becomes a little bit hard to figure out which one is which one. So I'm going to give these two halt instructions names. This is halt 0 and this is halt 1. Because in reality, one is representing what to do when you have an odd number in reg B, and then the other one is representing what you want to do when you have an even number in reg B. So halt 0 in this case is representing what we want to do when we have a even number in reg B, and then halt 1 is the one that is representing what we want to do when we have a odd number in reg B. Are we still doing okay so far? I just want to kind of check in and make sure that There are no questions at this point. And if there are any questions, go ahead, ask those questions now. Excellent. We got a bunch of people typing. That's always a good sign. Yep, that's my cat again. Alright, so Matt says, I didn't understand at first why the if-else statement mattered if they were both halt commands. Yeah, the halts are basically just placeholders because I don't want to complicate the program by the branches, what we do in each branch of the conditional statement. So Terence is correct. Matt is correct. But they are distinct halt instructions, so we need to have halt 0 and halt 1 placed correctly, when we are looking at this part of the code. Alright, so I knew that several people were typing, and Matt is the one that finished typing first. So we got Richard still typing, and I thought there was one more. Jonathan W. already finished typing. I thought that halt was 0, 1. So we just do 0, 1, 1 or 0, 1, 0 to distinguish. No, they're both just halt instructions. I'm just using a comment after the halt instruction to distinguish which one is which one. In other words, there's only one single halt instruction. But using the comment after the halt, we can distinguish which one is halt 0 and which one is halt 1. Alright. Alright, cool. We would need to define a label that would be after EQZ. That should be our else case. Well, there are several ways to do this. Part of the question is, do we want to maintain the ordering that the then branch is always in the program before the else branch? That's kind of a stylistic kind of thing, and I would say at this point of this class, maintaining that order is going to be handy, just because it makes the code easier to read and it's easier to correspond the assembly code with the C code. So we're going to try to maintain the ordering of the then branch versus the else branch. Alright, so now the question is, where is my then branch and where's my else branch? So when you go back to the C code, okay, this is the pseudo C code. This is the condition that we are checking, and this is our then branch. So that means once we confirm that this condition is true, then we should get to the then branch. So that means this is the then branch right here. Okay, so this is going to be our halt 0. Okay, so halt 0. And that means the else branch is actually right here. Okay, so if you want to save a few instructions and just say, okay, I want to make this code as short as possible, you could just put a halt 0 over here and you're done now. Okay, because we get to the correct halt instruction. However, if you do something like this, you're also inverting the positioning of the then statement versus the else statement. It is not so much of a problem with this really simplistic program because the then versus the else is really just which halt instruction are we talking about. It's not a big deal. On the other hand, if you're working with a much larger program, changing the ordering of the then versus the else branches sometimes can lead to some confusion because now the ordering of statements is different from your original C code. So given that is the case, okay, I'm going to put a JMPI over here to say what if it is not equaling to 0. So in that case, I'm going to define a new label which is not equal to 0 down here and say, okay, this is what we do for the else branch. We have halt 1 over here. And then Dalton said you could do a JMPI else and add another label. Exactly, except I didn't use the label name of else. Yep, but Dalton is 100% correct. That was the solution to that problem. And then Terrence said JCI jumps to the EQZ when the Z flag is set. When it is set. So JCI branches if and only if the Z flag is a 1. Because what JCI does, okay, let me label JCI here. What JCI does is to do something like this. PC gets Z and then question mark. If Z is a 1, it goes to whatever the program counter points to in RAM. Otherwise, it will just kind of add the program counter by 1. So that tells us that it will do the branch to the label, which is whatever the program counter is pointing to at that time, if and only if the Z flag is non-zero. So this part is kind of important too, because if you read column C in the opcode table, that would actually tell you, exactly how the JCI instruction works. All right. And then Jonathan W said, so this shows us how to do conditional logic in TTP. Exactly. Exactly. It's kind of ugly, right? But given, this very simplistic code that we have, the simplistic instructions that we have, this is what we can do. Now, what if I change this program a little bit? Okay, so instead of a halt here, I specify a no op. Now, no op is basically just no operation. That's all it does. It's absolutely nothing, and then it moves on to the next instruction. So if I change this, then you will go like, oh, okay, that's not too big of a deal. We just have to change all the halt instructions to no op instructions, right? So we change this to a no op. This is no op 0, and now this is no op 1. But now we have a problem, don't we? Because no op 0 is just going to say, oh, I'm going to do absolutely nothing and I'm going to move on. So after no op 0 is done, it's going to move on to no op 1, which is not what we want. Because in a conditional branch, after you execute whatever is in one of the two branches, you should be at the end of the entire conditional statement and not to execute the other branch. So in this case, we are falling through the then branch, which is what we are seeing here. No op 0 is our then branch. After the then branch is done, it will fall through into the else branch, which is incorrect. So now we need another unconditional branch, JMPI, to end if, okay? And end if is going to be defined all the way over here to indicate this is the actual end of the entire conditional statement. And now we can put a final halt instruction here because we want the program to stop. Alright, so in the text channel, we see Terrence is asking, can we do if else statement, or we can only do if else? Well, if you want a nested conditional statement, all you're doing is to change one of the two branches or both. You're just changing this one branch here into another conditional statement with about the same kind of structure. So we can nest as many levels as we want. It would just look really ugly. But in terms of whether we can do it or not, yeah, absolutely. Because we are talking about a structure that can embed another structure like this. The conditional statement, which is typically considered, well, actually the entire thing is the conditional statement, but the conditional part, the condition, is only this part here. And then we evaluate, which branch to, how to proceed, which branch to proceed to. That would be the job of these two instructions. And then we have the then branch specified over here, including the unconditional all the way to the end. And then we have the else branch specified over here. So that is the structure of a conditional statement, if else type of statement. It does not say that you cannot have another conditional statement, where no op is currently is, because remember this no op is really just a placeholder. It's basically saying, okay, I'm a stand-in for the then branch, okay, and this no op here is basically just a stand-in for the else branch. But each one can expand in a real program into its own structure. Okay, it can be a loop, can be another conditional statement, and so on and so forth. So I hope that answers Terrence's question. Alright, so Ivan said, why have JMPI to halt instead of having halt right after JZI? Because halt here is also just a placeholder. We have a whole bunch of placeholders because I just want to focus on the structure of this logic. So this halt is just a placeholder of whatever is coming after the conditional statement. In other words, this original program here in C, okay, this original program here, I need to make sure my face is not covering it. Okay, so this is really just one of the many statements in a program, right? We have no idea what is potentially after this conditional statement. So the halt instruction over here is really just representing, oh, okay, if we have additional statements to execute after this conditional statement, then the halt instruction will be replaced by those additional statements, or the assembly code for those additional statements. So I hope that answers Ivan's question. So the halt is basically just marking the end of the conditional statement. Now, if this conditional statement is really the only thing we need to do, fine, put a halt instruction here and we finish the entire code already. On the other hand, if after we determine whether register B is odd or even, we want to go this way, go the other way, but after doing those conditional things, we have some additional stuff to do, then the additional stuff to do is going to be replacing the halt instruction, because that's basically just representing what we need to do after the conditional statement. I'm just looking at the time. Okay, so now we are looking into the shortcut. Okay, so the shortcut is based on the architecture itself. So the shortcut is looking into the ALU, and we look at the AND operation, right? So the AND operation is this guy over here. The output of the AND is going into the multiplexer, and then the multiplexer is going to go into here. So you can see immediately that regardless of which operation we perform, the output or the result of the operation is always going to affect the Z flag and always going to affect the S flag. So if that is the case, that means the Z flag is automatically already set or reset, cleared, after the AND operation. There's no need to compare with 0 afterwards, because if all we need to know is whether it's a 0 or not, is already determined by the time we are done with this instruction. We already know whether the result of the AND is a 0 or not. There is no need to perform the actual compare. So these two instructions are actually not needed here at all. So let me just kind of comment out these two, to basically, emphasize that you can put these two in, but it doesn't do a single thing for you. It doesn't add anything to it. It doesn't make it wrong either. It's just not needed. So let me just kind of go back up a little bit and see if anyone has any question of why these two instructions are really not needed, even though putting them here is not going to harm anything, but they're really not needed. All right. So the AND operation conjunction changes the Z flag. Yes, absolutely. That's kind of the whole point of digging into the ALU, because we can see how any of the 6 operations here will affect the sign flag, which is just the most significant bit of the result, and also the Z flag, which is the NOR of all of the bits of the result. Now, just because these two tunnels are affected doesn't mean it's going to be stored into the flags register, because all that means is the Z flag here is going to be influenced by the operation, and then the sign flag here is also going to be influenced by the operation. But when you look at the output of the ALU, and you look at flags out here, which is the red line at this point, it goes into the flags register. So the only thing that would not affect the flags register are increment and decrement. Those two are very special instructions. They are designed specifically not to affect the flags register. And I will explain why we need to go through all the hoops just to make sure that increment and decrement, they do not affect the flags register. But anything else, okay, any other operation that involves the use of the ALU, the arithmetic and logic unit, will influence at least those two flags in the flags register. So the sign flag and the Z flags are both guaranteed to be impacted by the result of an operation after anything other than an increment or a decrement. Alright, so I think we got some more text traffic here. So Jonathan said, so the AND operation changes the Z flag? Yes. Matt said, and the Z and the S flag? Yes. And then Terrence said, so the Z flag gets influenced, but how do we know its value we need it? How do we know it's the value we need it to be? JZI is the only way to tell. So the only way to see whether the Z flag is a 0 or 1 is whether JZI performs the branch or not. So I hope that answers Terrence's question. And this is why we talked about all of those flags when we talked about binary subtraction, because when we need to see whether a register is less than another register, that's when we need to use JCI or JLI, depending on whether we are looking at signed versus unsigned values. If we want to see if two values are exactly the same after a compare, we look at the Z flag. Okay, the O flag by itself is usually not very useful, because we just go like, it's meaningful, but only in the context of being one of the components that we need in order to determine the L flag. The sign flag, on the other hand, is useful on its own. Okay, it is useful on its own because the sign flag alone can tell you what is the sign of the result of an operation. And by the way, that is also what you need for today's lab. Before anyone asks, do we have a lab today? Yes, we do have a lab today. The passcode is ABS. It is not anti-lock brake system. It is just absolute value. So that's it. Okay, I think I have completed everything that I need to do for today's lecture, and you have enough material that you need to understand to do the lab. In fact, I gave you actually quite a bit of information in order to do your lab. This final version of this code here is related to what you need to do with your lab, but your lab has it's a little bit more complicated. It kind of goes back to two's complement when we talked about signed values. How you use two's complement in order to invert the sign of the value being represented in a signed integer. So you kind of have to go back to that a little bit and find out what instructions you need to use in order to implement two's complement. Absolutely. To get a copy of the Joplin note. So let me do that. The quickest way, do you guys, can you deal with a PDF? Because the easiest way is to print it to a PDF, because that way, I can isolate just one note, because otherwise I can export the entire notebook, which is a bunch. Anything works. Okay, alright. Because I'm not sure whether you guys want to perform additional editing, in Joplin, or whether you just want an output of the whole thing. Okay, PDF then. PDF it is. Alrighty. So print to file. I see. Alrighty. Alright, so I'm gonna attach the PDF into the text channel. So for those of you who are interested, this is the Joplin note for today. And I'm going to make one for the one from the previous class, so this way you guys can also um, re-examine, how I denote, changes of the nodes inside the processor, and also not the processor, for the device that we are tracking, and also how to denote changes after propagational delay. So that's one, and I'm going to give you the other one too. Yeah, you guys can sign up if you want to. I'm just talking to myself when I'm printing the notes to PDF. Yeah, so you can move on to your lab, and I'm just gonna do what I need to do here. But if you do have any questions, go ahead and ask those questions. Alright, so here's the other file. This is revised to show another way to track propagation changes. Change propagation. Alright, there you go. So now you have both the Joplin note for today and also the revision of the Joplin note from last Thursday. And then this Thursday is our exam too, so don't forget about that, okay? Alright, so without any additional questions, I'm gonna get off of the voice channel and turn off the streaming, but I'll still be online, so that if you have any questions about the lab, I'll be here to answer those questions.